Alright people, welcome back. So in today's episode, we are given a grid m times n. This problem is called minimum path sum, and this grid is filled with non-negative numbers, and we must find a path from top left to bottom right, which minimizes the sum of all numbers along its path. You can only move either down or right at any point in time. Okay. So in a sense, it's close to the one we did last time, where we had to compute all the possible paths moving right and down. And it's also close to the house robber problem, because we need not in this case to maximize, but to minimize. So for example, without seeing what is written here, can we... okay, so what's the minimum sum? 1, 3, 1, 1... okay, that is why it is highlighted. Okay, so yes, this is the minimum sum, because the sum is 4, 5, 6, 7. So it's 7, and while, for example, if we pass here, or if we pass here, or if we pass here, we get to 4, 2, or 5, which increase our sum. So the input grid is a list of lists. For example, here, what's the best way to proceed? So can we do 1, 2, 3, 6? Yes, and that's exactly why we get 12. Yes, got it. Crazy. Okay, first thing that comes to my mind, just calculate all the possible paths and then return the minimum. How do we do so? Actually, no. Maybe we can do a dynamic programming approach, which is actually what I think we have to do, which is, okay, so this is what you pay at the beginning, which is 1. Then let's say that we move 1 this direction. So in general, to get, for example, to this 5, you can do 2 paths, which are these 3, okay? These 2, sorry, okay? So now the question is, the cost for a path is equal to 1 plus 3 plus 5 or 1 plus 1 plus 5. So for example, if I start to the end, and for example, I have the minimum cost to reach 2 and the minimum cost to reach this 1, I can calculate the minimum cost to get to this 2 as the minimum between this or this plus 1, of course, which is the cost that I pay to arrive here. And here I can do the same, like this minimum is equal to this minimum plus this minimum. And this minimum is equal to, the minimum between these two minimums, and that's the same I get here to get to my minimum for 2. But the question is, once I am at 1, how do I get there? The minimum cost at 1 is equal to the minimum cost at 3 plus 1. So how do I implement that in code? So it's like dp ij is equal to dp of ij minus 1 plus dp I minus 1 dpj plus the cost. So it's like grid ij. That's the formula. And I think I can do this for I in range. Actually, I don't have neither m or n, so I can say m is equal to the length of the grid and n is equal to the length of grid 0, let's say. So for I in range m and for j in range n, that's what I'm about to do. I can't do a for loop because I can't move this way. I need to move like diagonally, like 0, 0, then I increase 1, 1. So how should I proceed? Okay, so here, okay. I think we can do this way. So this for loop is okay. Of course, here we need the minimum. It's not a sum. It's a minimum. It's literally a minimum. So what did I write here? That's nonsense. Okay. Now I've got, I want this minimum. I think I already explained why. But of course, what's the problem here? The problem is I am proceeding this way, but it doesn't work because I didn't really update, I didn't really initialize anything. So at this point, I think I can do range, and here I can do 1m, 1n. And why do I do 1? Because I already want to initialize this. Okay, so I need to initialize the dp, the grid, the matrix. So I think I can do this by doing 0 times n. this must be a list of lists. So this should be for underscore in range m. So this is a list like a m list of length n. Yes. And now what do? I basically want to do for I in range m. So I'm going now. Let's do for j in range n. dp 0 j. No. Yes, that's exactly what I want. dp0j must be equal to dp0j minus 1 plus grid j, 0j. So I'm basically creating the grid until now, and I can do the same here. dp0, not 0, I 0 is equal to, same stuff here, just interchanged. So here we write I minus 1, 0, and j like an I minus 1, 0. Sorry, this is not I minus 1. So we're basically calculating this and this, because once we calculate this, then we can calculate everything else. Like we can calculate 1 by this, and this 5 can be calculated by 3 and 1, and we can go on like this way. And I think we can run at this point. What's missing here? Perhaps you forgot the comma. Did I? No, the comma is there. No, the comma is there, man. Literally. Here there is a D though. So the D we don't like. Okay, fantastic. The output is null, but that's very easy. That's because we didn't return the how should we create the maximum? So for list let's call it for L in dp. No, actually we want to return, no, this makes no sense. We want to return dp, and then we do m n minus 1. That's crazy that it works. I can't believe this works. Okay, it doesn't actually. Okay, fantastic. But we passed 64 out of 66 cases, so let's see what was missing. So the case that we return 2 here instead, we must of course return 1. So I don't know if this matters, but I think here it must start at 1. Let me just check if this creates problem. Damn, this actually creates a lot of problems. Maybe because I didn't write M here. Now everything is incorrect. That's crazy. What's wrong? What's wrong here? So we start with dp is equal to 0, and then each time we increase, like okay, but maybe the problem is that we are not defining the initial cost. Like dp00 must be grid 0, even though I think we are already setting this, aren't we? So for j equal to 1, no, we're not setting that. So I think, okay, now it works. Let's go, guys. It works. So the problem was that we were not initializing the first element on the top left of our matrix, and so the entire algorithm didn't work. Okay, nice. So the idea here was to calculate the minimum cost at the, like here at the corner, has the minimum between the minimum cost at the 2 adjacent cells, plus of course the cost of the cell. And each cell could be calculated the same way, but the main bottleneck, the main problem was that once, for example, we are here or here, we can't do that anymore because there is no cell here. So we have to initialize those cells. So basically we initialize these 5 cells, and then once they're ready, we can compute the rest automatically. Now, in terms of time complexity, this is O(n) times m. And in terms of memory complexity, it's m times n. So I wouldn't say that is great. Actually, I think can be improved, either memory-wise or time, like in terms of time complexity. So what I was thinking, guys, is that maybe we can actually override the grid. So the idea is that to save on memory, we can override the grid. Like instead of using the DP, we use directly the grid, and so we rewrite the grid every time. So maybe we could save memory, but I'm not sure that this would be something that someone would like to have, because that's actually the input. So if someone you actually lose the input at the end. I don't know if this is something that we should aim to. So at this point, I think we can conclude, actually. We can stop here because I'm not sure I want to go for the grid override solution. So at this point, guys, thank you very much for watching this video and see you in the next episode.